Welcome back. Now, last time the main point was that mathematics, and especially the math of the harmonic sequence, informs which notes you might want to include in a scale. Today we're continuing talking about scales. Today we're going to talk about how mathematics informs the tuning of those notes. Very small changes in tuning. We're talking about exactly which frequencies we choose to put on a particular scale. We're also going to talk about what a profound impact those small changes have on composition, because one of the main points today is about the coevolution of scale tunings and musical composition in Western classical music. But let's start with a little bit of music. I want to play two pieces here at the beginning. Now, these are both from the Western classical music tradition. The first is the Allemande from Partita No. 2. This was composed in about 1720. This is the first movement of the partita. The last movement is the chaconne that I was asked about in my interview at St. Mary's College. The other piece I want to talk about is David Frome. It's from his Sonata for Violin Solo. It was composed in 2004. I want you to think about what makes these so different. How did we get from Baroque-style music to 20th century music like the Frome? How does mathematics play a role in this change? First, let's hear a little Bach. That's Bach. And now let's move forward a couple of centuries to the Frome. This is the Sonata for Violin Solo, 2004. What makes those pieces so very different? How did we get from this Bach style, this Baroque style, where we start in one key and we modulate to another related key, and then we come back? And then we get to Frome, the 20th century music. There's seemingly no tonal center. There's no reference note. It's not based on a single scale. It's not a sonata in A minor or D major. It's just a sonata because there's no tonal center. How does mathematics play a role in this change? And I think it's surprising that it's important exactly how you tune the scales, that small changes in scale tunings make such a big difference. Let's quickly review what we talked about last time. We were choosing notes on a scale, and we were using math in the overtone series to inform our choice of those notes. How many notes, which ones, and how those choices gave different moods and styles. And we saw toward the end how a piano is never in tune. Now, there were two key methods we talked about last time. We talked about choosing notes based on the overtones of a single fundamental. That was the idea of having a fixed reference point and basing everything on that. And the second method was having overtones of one note inform the next note, and then using the overtones of that note to get the next, bootstrapping. Today's lecture is again in three parts. The first part, we're going to talk about calculating exact pitches. These are called tunings and temperaments. Exactly what frequency should we put these notes at? This is essentially the question, where exactly should I put my fingers on the strings in order to play a major scale? It's also the same thing as where should you put the holes on a flute, or how long should the pipes be on a xylophone, things like that. The second thing we're going to talk about is why are there 12 keys per octave on Western music and on our piano, and not some other number? Why 12? And the third thing we're going to talk about is how subtle changes in tunings mirror the changes in composition over the last few hundred years of Western music. We really want to understand this mathematical difference between Baroque music and 20th century music. We're also going to get a couple of fascinating little asides. Along the way, we're going to find out why playing in a music ensemble is so hard. We're also going to find out why there's so little classical music written for guitar and piano. And finally, we're going to figure out how piano tuners get around the fact that they can't tune a piano perfectly. This is really foreshadowing the next lecture, which is on dissonance and piano tuning. Now, we remember that objects vibrate in different modes, and we've known now very well that those frequencies are in a ratio of 1 to 2 to 3 to 4 to 5, and the wavelengths are in a ratio of 1, 1/2, 1/3, 1/4. What we learned from the overtone series is that to go up an octave, you multiply the frequencies by 2, and to go down an octave, you divide by 2. You can see that in the chart of the overtones, looking from the first to the second, the first harmonic to the second harmonic, or from the second harmonic to the fourth harmonic. We also see that to go up a fifth, you multiply the frequencies by 3/2. The fifth, member, is 7 keys on a piano, or it's the fifth note on the major scale of the bottom note. And you can see that in the chart of the harmonics, looking from the second to the third harmonic, or from the fourth to the sixth harmonic. Now, before we dig into these tunings, a word of warning about this, and this is from J. Murray Barber. He wrote a 1967 tome on the topic of tunings. This is what he said. Explanations of tuning of the musical scale are usually so full of figures that the non-mathematician shies away from them in terror. This is unfortunate, for the subject is not only of interest to the musicologist and the theorist, but of immediate and practical concern to the performer. That's quite the warning. But we're going to do our best to make this challenging topic as simple as clear as possible. So let's start by finding the frequencies of an A major scale. Where exactly should I put my fingers on the strings to play an A major scale? We're going to come up with actually 3 different answers. We talked about 2 of them last time. Just tuning, where you're using the overtones of the fundamental. And we're going to talk about why it matters when you're playing music, this just tuning. We're also going to talk about Pythagorean tuning, which is using this bootstrapping idea from getting from one to the next. And finally, we're going to talk about equal tempered tuning, which is modern piano tuning. Let's go back to just tuning, which we talked about last time. Remember, this was really great for some instruments, bagpipes, sitars. It was good for some musical traditions where there was no modulation, no key change, like Indian music. Now, pianos are never in tune, in part because we try to modulate. Essentially, bootstrapping is modulating. You're starting at the low A and you're taking the fifth of that, and then you're modulating into that key to find the fifth note on that. What we'll see is that the problems with tuning pianos gave rise to a slow evolution of tunings, and those mirror these changes in composition. Now, if you're using just tuning, there's really no problem. There's no evolution of tunings needed. You can always just tune things exactly in tune with the fundamental. There's no companion changes in composition because of that. So let's calculate the exact frequencies on a just scale. In order to do that, we're going to use the overtones to get frequencies of the scale. We're going to take these overtones, and they're in the wrong octave, and we're going to bring them back down into the correct octave. We're going to generate as many notes as we want, and we've seen the solutions, and this is what we get if we take a 7-note scale. Now, the problem with this scale is that while the notes were in tune with A, with the fundamental, they weren't in tune with each other. And let's look at the F sharp. Now, if you remember, the F sharp we got originally for a pentatonic scale, that was a different F sharp. That one was not in our 12-note scale. This F sharp is in our 12-note scale. It's not the 7th harmonic. So a just tuned F sharp is related to the ratio 5/3. The frequency should be 5/3 times whatever the fundamental is. That's about 1.667. The overtones of B include an F sharp, and we figured out the frequency for B. B is related to the ratio 9/8. And so the overtones of B, well, the first overtone is going to be 2 times that. That's going to be 18/8 or 9/4. And the second one is going to be an F sharp. It's actually an F sharp 6. And that is going to be 3 times the fundamental B. And so we're going to get 9/8 times 3, or 27/8. Now, an F sharp 5, if we want to get an F sharp 5, we take the F sharp 6 and we divide by 2, and we get 27/16, or about 1.688. And this is why playing in an ensemble is hard. You see, the F sharp that's written on your page, I remember it was my high school music teacher, it was Mrs. Watruba, who always said, you have to listen to everybody around you. And at the time, I sort of thought that what she meant is, to keep rhythm with everybody, you have to listen to everything around you. But it's more than just that. You see, if there's an F sharp on my page, then I actually need to play a different note if everybody around me is in the key of A than if everybody around me is in the key of B. If everybody around me is in the key of A, my F sharp should be at 1.667. If everybody around me is in the key of B, I should play a different note, 1.688 roughly. What's going on here is that there's a fundamental problem. You can't create a scale so that the overtones of one note exactly match up with the other notes, even just with 3 notes. The additive structure of the overtones really conflicts with the multiplicative structure of intervals. You might think this is just a problem with pianos or other fixed-tuned instruments like organs and xylophones, but that's actually not the case. What the mathematics is telling us is that no instrument can play A, B, and F sharp so that they're all in tune with each other. This isn't a problem of implementation. It's not a problem of a particular instrument. It's actually a problem of theory. It's a problem of the mathematics. No instrument can make it work. In fact, string quartets know this. Despite having a lot of tonal freedom, you can adjust a note a lot. You can adjust it very slightly on a string instrument. But they do tune their open strings, and when you hear a string quartet tuning up, everybody matches their A's, and then the violin tunes up a fifth to an E, and the cello and viola tune down fifths to a D, G, and finally a C. And the next thing a string quartet will do is they'll check the low C against the high E. And if they've been tuning perfect fifths, they'll find out that the low C and the high E are not in tune. This is the fundamental problem that we're dealing with. So let's move on and talk about, from just tuning, let's talk about Pythagorean tuning. Now this is of course named after Pythagoras of Samos. He founded Pythagoreanism, a religion, and his life is really shrouded in mystery. We don't have a whole lot of historical records about exactly who Pythagoras was and what he did. His followers tended to attribute many, many things to him, and whether or not those are true, it's really not known. The Pythagoreans believed that all numbers could be written as fractions, as rational numbers. They didn't think that there existed numbers like the square root of 2. Square root of 2 is not written as a fraction. You cannot do that. Now, there's really no evidence that Pythagoras actually proved what he's most famous for today, the Pythagorean theorem. Of course, like a lot of mathematical theorems, there's a lot of evidence that other people knew the Pythagorean theorem long before Pythagoras was ever born. The musical ideas of the Pythagoreans were that notes were pleasing together if the ratio of frequencies is a fraction with really small numbers. And so they prized things like the octave with its 2-to-1 ratio and the fifth with its 3-to-2 ratio, but especially the fifth. And that's what's key in Pythagorean tuning. The goal in Pythagorean tuning is to keep the fifths exactly in tune. And what we're doing when we tune Pythagorean scales is we're walking around what's called the circle of fifths. From one note to the next, we're going to go up a fifth. Remember, that was 7 half steps, or 7 keys on a piano. It's also going from the fundamental to the fifth note on that major scale. A natural question you should ask is, why is the circle of fifths a circle? In the Western tradition, we have 12 notes on that circle of fifths. We start at A, and finally we get back to A 12 notes later. We're going to talk more about why it's 12 later, but first let's take a trip around the circle of fifths. Let's start on A, and the fifth note on the A major scale is E, and the fifth note on that scale is B, and then F sharp, and then C sharp. And you see, we're just walking around this circle. We can also go backwards. To go backwards, we're asking, what's a fifth below A? And we get D. In other words, an A is the fifth note on the D major scale. Now recall, to go up an octave was multiplying by 2, down an octave was dividing by 2, and up a fifth was multiplying by 3/2. So if we start at an A4 at 440 hertz, let's think of that as just 1 and work in relation to that frequency. We're looking for notes between A4 and A5. We're looking to put scale notes in between A4 and A5 to tune our scale. Really, that's between 440 hertz and 880 hertz, which is the octave above an A4. But in terms of our fundamental at 1, we're thinking of just getting numbers between 1 and 2, so that in relation to the A at 440, the numbers are just between 1 and 2. So we can do that with our circle of fifths, and I just want to work through an example. A C sharp, let's see if we could find the C sharp on our scale. Now to get a C sharp, it looks on our scale like we have to go up 4 fifths. To go up 4 fifths, we would be multiplying by 3/2 4 times, so that's multiplying by 3/2 to the 4th. Now that doesn't get us to the correct C sharp, that gets us to C sharp 7. We have to go back 2 octaves to get down to C sharp 5, the one that we want. That's dividing by 2 each time. And so now we found our C sharp, we should multiply by 3/2 to the 4th and then divide by 2 squared. We can simplify that. It's 3 to the 4th over 2 to the 6th, and with a calculator that comes out to about 1.266. We can do exactly that, and we can work through the details, and we can come up with an A major scale where the fifths are tuned exactly perfectly. And when we do that, we get this. I love the G sharp sitting there at 128 over 243. Now for comparison, the C-sharp in adjust scale was 4/5 or 0.8, whereas the C-sharp in our Pythagorean scale is 64/81, which is about 0.79. Those are quite different. So we can do that. We can start tuning at the A, and if you think about it on a piano, we can start tuning at A, and we can go up 12/5. And if you remember last time, the problem with piano tuning was that going up 12/5 was different from going up 7 octaves, although it ended you up at the same key. And that was the problem last time. 3/2 to the 12th was not the same thing as 2 to the 7th. That gap is actually called the Pythagorean comma, the gap between 12/5 and 7 octaves. And we now know where it gets its name. If you tune scales in a Pythagorean way, that's the gap you're left with at the end. Is that a big problem? Is that gap noticeable? Let's hear it. So musicians measure the space between two notes, not only in half steps and things like that, but when we're talking about fine distinctions, we actually measure them in what are called cents. 1 half step, just going from one key to the next on a piano, is 100 cents, and therefore to go up an octave, you have to go up 1,200 cents. Now, remember that everything has to be multiplicative because we're talking about intervals, and these cents have to be multiplicative, and so 1 cent is actually equivalent to the ratio 2 raised to the 1 over 1,200. And if we do that, then when we go up 1,200 cents, we're multiplying that number times itself 1,200 times. The 1,200s cancel, and we just get 2. We just get an octave. And if you think about it this way, 100 cents is then going to be 2 to the 1/12th power, and that's going to be a half step. And we'll see that number again in a bit. The Pythagorean comma, if you do the calculation, turns out to be about 23 cents. So that's about 1/4 of a step between one note and the next on a piano. What does that sound like? Let's put that gap of 23 cents at an A440, and let's play it with sine waves. So the traditional A4 is a 440 hertz A. Let's hear that. And then this gap, if we put that gap there, we would get 446.39 roughly hertz. Let's hear that. Now you might think that that sounds small. It turns out that even though that's small, it's incredibly important. Just to see how important it is, let's play them at exactly the same time. There we hear beats again. We've heard those before, and we'll talk about those more later. That gap has actually led to big changes in composition, and we're going to talk about that. So how would we fix that, this big problem with this gap? There are actually many different solutions. I should put that in quotes, solutions, because there are no exact solutions, but there are many different ways of what's called tempering the gap, and that's how we get the name temperaments. Pythagorean tuning, you take that entire gap and you put it in 1/5. You take that last fifth and that has the entire gap. Other tunings and temperaments, we use these words interchangeably mostly. Other tunings and temperaments spread that gap out among more of the fifths. So other fifths are not perfect 3/2 ratios, but that means you don't have such a big gap at the end for your last one. What you're doing when you spread that gap out more is that keyboards are going to sound good in more different keys. You could play a piece in A or C or F sharp, lots more keys, and it would still sound fairly good. Spreading that gap out more gave composers more flexibility. And you can already sense this sort of progression, this evolution. When composers have more flexibility, they're going to move, you can think about the progression from Baroque music all the way through Romantic to 20th century music. So what's a modern solution to this tuning problem? Modern tuning, starting a little bit before, but by 1900 on pianos, spread that gap out completely evenly. Every fifth on a modern tuned piano, an equal tempered tuned piano, is equally out of tune. Now remember, the big problem here was that 3/2 to the 12th was not the same thing as 2 to the 7th. Mathematically, we can solve this by replacing 3/2 with some number, let's call it r. And the equation we would want to be true is that r to the 12th, if we take the fifth and we replace that 3/2 with r, 12 of those, we want that to exactly equal 2 to the 7th. We want to hit that octave exactly. Well, r to the 12th equals 2 to the 7th. That's a fairly easy equation to solve. We just have to take 12th roots of both sides. And we get an answer of r is equal to 2 to the 7/12. When you plug that into a calculator, you get about 1.4983. Notice that that's really close to 1.5. It's a little bit less than 1.5. But also, if you think about it, that value of r is irrational. And that's why I talk about this as being math not making modern music mad, but math making modern music irrational. That value of r cannot be written as a fraction. The Pythagoreans didn't think that numbers like this existed. Let's take this in another perspective. If we divide the octave into 12 equal half steps, remember multiplicatively, not additively, then each one should have a ratio of 2 to the 1/12. Remember, that was exactly 100 cents. And if each half step had the ratio of 2 to the 1/12, then 7 of them would have a ratio of 2 to the 7/12, which is the number that we just got. So let's use this number to construct a scale. We're going to start again with a 440 Hertz A, and now we're going to find the other notes. And I'll just walk through one example. If we want to find our C sharp, remember that's up 4/5 and then down 2 octaves. And so we would take our 440 Hertz A, and we would go up 4/5. That's our key number R raised to the 4th power. And then down 2 octaves would mean dividing by 4. And when we do that calculation, we get 554.36 Hertz, roughly. Now remember that a just C sharp was at 5/4 of the fundamental, and that gives us a 550 Hertz note. So let's compare the 3 different C sharps that we have. We have a just C sharp, we have a Pythagorean C sharp, and we have an equal tempered C sharp. How different are they? With the A at 440, the just C sharp was 550 Hertz exactly. The Pythagorean C sharp was 556.89, roughly. And that, when you talk about Pythagorean scales, you talk about the impossibly high major thirds. And this is a very sharp note to the ear. And the equal tempered C sharp is going to be at 554.36 Hertz, about. Now let's listen to these. First, here's a just C sharp at 550 Hertz. Next, let's listen to the Pythagorean, the highest of these. And you can probably tell that's sharper, it's higher in pitch. And finally, the equal tempered C sharp is in between. Let's compare the just and the Pythagorean. That's how we get this impossibly high major thirds note. And when we play those together, you hear the beats, you hear the dissonance, the unpleasant pitches. There's tension in there. And that dissonance is going to be the subject of the next lecture. So now that we've tuned our scales, we have 3 different ways. But we've tuned our scales, and now we've settled, at least in modern times, on an equal tempered system. Now let's move on and ask, why is it 12 notes on our equal tempered system and not a different number of notes? These 12 notes that we have on our equal tempered scale are equally spaced. We can ask the very mathematical question, would another number work better? Now, there might be lots of cultural reasons why we ended up at 12, but let's think about this mathematically, and let's just start from scratch with no culture involved. Let's just build a scale and see where we get. And let's build a scale with equal spacing. That gives us maximum flexibility. If we have equal spacing, then we can modulate into any key we want, and that's a really nice feature of Western music. Now, there are notes that we definitely want in our scale. And that's because when we hear anything vibrating, we hear its first few overtones very clearly. We hear the octave, we hear the fifth, and then the difference between the fifth and the octave, that gap is a fourth. And we also hear up to the fifth harmonic, which is a major third. And so those intervals are really important. So suppose the fundamental is at 100 Hertz. In just tuning, which sounds best, the octave is going to be double that. The fifth is going to be 3/2 that. The fourth is going to be 4/3, and the major third is going to be 5/4. Those are the notes that sound best. Those are the just notes. Those are when we're tuning perfectly in tune with the fundamental. And those are the key fractions we're going to look at. 3/2 is 1.5, 4/3, 1.3333 repeating, and 5/4 at 1.25. This is a mathematical question. For what values of n will a scale with n equally spaced notes include notes that are really close to these key fractions? So let's work by trial and error and see. Now if we have 2 notes, that's the fundamental and the octave, right? If we add a second note to our scale, so we get a fundamental, 1 note in between, and then the octave, that note needs to be exactly halfway in between. And if we do the calculation, we get, it's what we call on our scale the tritone, the augmented fourth. We heard about this. It's the beginning of Maria or The Simpsons. It's actually also, it was originally called the devil's interval. If we have 3 notes, then we're going to put a fundamental and 2 notes before we get to the octave. And when we look at those, we get close to the major third, but we don't get close to the 4th or 5th. Let's listen to those. If we have 4 notes in our scale, nothing is close to the key notes that we're looking for. If we have 5 notes, you can see that we get close to the 4th and the 5th, but we don't get very close to the major third. If we have 6 notes, 7 notes, 8 notes, you see that we can get close to some of these ratios that we're really looking for, but we can't get close to all 3 of these with any one of these systems. Let's keep adding notes. 9 notes, 10 notes, 11 notes, still nothing close. 12 notes. With 12 notes, look how close we are. We're actually very close to all 3 of the key things that we want to hit. The 5th of the 12 notes is very close to the major third. It's 125.99 approximately. Remember, that's very close to the 125 we were aiming for. The 6th of the 12 notes is near the 4th. That's 133.48. That's what you get. The just value was 133.33 repeating. The 8th of the 12 notes was really close to the 5th. The 8th of those notes is at about 149.83. Remember, the value we were aiming for is 150. With 12 equally spaced notes, we get very close to all of the important ones we want. What is it that we learned from this? We learned that if you want equally spaced notes, and that allows for modulation and key changes, and if you want to match up with the most prominent overtones, the major third, the 4th, and the 5th, you need at least 12 notes. And we figured that out sort of by going from the beginning with trial and error. Let's try to resolve this problem in a different way using some mathematical theory, not trial and error. Now, this is really cool, but slightly complicated math. It's really worth it to listen to this and to try to understand. Remember, a just 5th is the ratio 3 halves. And we want to figure out an equally spaced system that would get really close to that 5th. If we were to place n equally spaced notes, remember these are multiplicatively spaced, they would have relative frequency, the fundamental, 1, and then 2 to the 1 over n, 2 to the 2 over n, 3 over n, all the way up so that when we had n of those, we would get 2 to the n over n, which is just 2, and we would be at the octave. Remember that for our 12-note scale, each half step was 2 to the 1/12th. And so this is just a generalization of that for n notes. Now, if we got close to the 5th, it would mean that, say, the kth one of those was really close to the 5th. In other words, 2 to the k over n was very close to 3 halves. Now, we can multiply both sides of that equation by 2. And then we can do what's called taking the log base 2. And what we get is that the log base 2 of 3 needs to be very close to k over n plus 1. In other words, we need a fraction, k over n, which is very close to log base 2 of 3 minus 1. We're looking for really a rational approximation of the log base 2 of 3. Now, there's lots of mathematics that's been built up to do things like rational approximations. So let's look at some of that. Here, rational means ratio or fraction, and rational approximation means we're trying to get close to an irrational number using just rationals, using just fractions. There's sort of an astonishing connection here to something called continued fractions. Now, a continued fraction is a fraction that has a denominator, and that denominator includes a fraction that has a denominator, and that denominator includes a fraction that has a denominator. It keeps going again and again. It's actually sort of self-referential. We'll talk more about that in Lecture 9. Now, the most famous continued fraction is one called the golden ratio. It comes up in the strangest places. It comes up in Fibonacci numbers, art, architecture. It actually comes up in pine cones, sunflowers, pineapples. It's really an amazing thing. And the golden ratio, when you usually see it written, you see it written as phi, and it's equal to 1 plus the square root of 5 divided by 2. If we write that as a continued fraction, it's all ones. You just get ones down, 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 down to infinity in this continued fraction. Let's look at some other continued fractions. Probably the easiest irrational number to get is the square root of 2, which is approximately 1.414. If we write square root of 2 as a continued fraction, here's what we get. It starts with a 1, and then we get a bunch of 2's, 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 all the way down. It's actually a nice algebraic exercise that I invite you to take on to prove that this formula is equal to the square root of 2 and that the last formula is actually equal to 5. Now, if we want an approximation of square root of 2, we can use this continued fraction. And the idea is that all we have to do is stop the fraction at some point. Just cut off the rest. If we stop after 2 layers of our fraction, we get 1.4. That's not too bad. If we stop after 3 layers, we get 1.417. That's getting closer. Remember, square root of 2 is 1.414, on and on and on. If we stop after 4 layers, we get 1.4138. We're getting very close. And you can see that as we take more and more layers of our continued fraction, we're approximating the square root of 2. That's the whole point of continued fractions, that they give us a nice rational approximation. So back to music. We wanted to get close to the fifth, which was 3 halves. And to do that, we needed a fraction which was close to the log base 2 of 3. Now, the log base 2 of 3, if you plug it into a calculator, is about 1.58496. So let's find the continued fraction for the log base 2 of 3. And here, this is what we get. Now, you can see it's not quite as simple as the other 2 continued fractions that we've seen, but it works the same way. And if we want a rational approximation, we're really just asking the question, where should we cut off this fraction? If we stop after 2 layers, the number we get is 3 halves. That's not a very good approximation of 1.58496. If we stop after 3 layers, we get 8 fifths, which is 1.6. That's a little bit better. Let's see what happens when we take one more. When we take 4 layers, this is what the continued fraction looks like, and the value of it is 19 twelfths. It's 1.583. That's getting quite close to the actual value of the log base 2 of 3. So let's stop there for a second. What would it mean musically to take this as our rational approximation? Well, it would mean that we are approximating log base 2 of 3 with 19 twelfths. And when we invert the log, we're taking exponentials, and so that would mean that 2 to the 19 twelfths is approximately 3. We can divide both sides of that equation by 2, and we get that 2 to the 7 twelfths is approximately 3 halves. That's familiar, isn't it? That's saying that one way to approximate 3 halves, remember, that's the just tuned fifth, is to use 2 to the 7 twelfths. That was the equal tempered fifth. In other words, this continued fraction just gave us the equal tempered 12-note system that we have in Western music today. Now you can ask the question, what would have happened if we had taken one more layer of fractions? Isn't that sort of curious? What would our musical system look like if we had just added one more layer? When we do that in the continued fraction, we end up getting 65 41sts. And that gives us the approximation that 2 to the 24 41sts is approximately 3 halves. Think about that musically. We would need 41 keys between one octave and the next. And the 24th of those would be very close to a perfect fifth. How close would it be? Well, our equal tempered fifth, the 2 to the 7 twelfths, is about 1.498. Now that's quite close to 1.5. If we had chosen 41 keys per octave, if we had taken another layer in our continued fraction, then the 24th one would be at 1.500419 approximately. That would be incredibly close to 1.5. That difference is almost inaudible. What would this mean for music? Think about what keyboards would look like. 41 keys in between octaves. On a piano, you can reach an octave. You couldn't really reach 41 keys. Think about what harps would look like, or xylophones. Everything would be much bigger. Wind instruments would have to have many, many holes everywhere. It would be very difficult to make them. There are even implications for music theory. Let's think about what the circle of fifths would look like. Remember, the circle of fifths was going up a fifth 12 times, and that got you back to A. If we had 41 notes per octave, you would have to go up 41 fifths to get you back. If you want to do the math, you should think about it. Going to the 24th note and then the 24th note of that, when do you get back really close to the original? And it would be after 41 times. What you would come back would be much closer to hitting to some octave above A than with our 12-note system, but you would have to go 41 things all the way around your circle. Now, some people do actually do some work with these non-standard systems, and it leads to some really strange-looking instruments. If you want to see one of those, one is called the tonal plexus. It has 211 keys per octave, and it looks very strange, and it's very difficult. It's interesting to listen to. Now I want to wrap up this little mathematical excursion into rational approximation because that was really complicated. So let's make sure we understand what we just did. We just took a little excursion into a world with more than 12 notes per octave. And the mathematics says this: if you want to get a better and better approximation, if you want a note that's closer and closer to the pure fifth of 3/2, what you should do is keep taking more layers in your continued fraction. And as you do that, the advantage is that some notes are much better in tune. You're getting closer to the just system, which is perfect. The disadvantage is that you have too many notes in each octave. Instead of 12 notes, you have 41 notes. I mean, take your pick, 12 notes per octave or 41 notes. I'll stick with 12. You know, I can honestly barely hear the difference between two neighboring notes on a 41-note octave. Now, the last point I want to get to is, why do tunings matter? And to address that, let's go back to the 12-note scales and the different tunings we talked about: the just tuning, the Pythagorean tuning, and equal-tempered tuning. Now, those weren't actually that different. So really, why should we care so much? You see, different tunings sound a little bit different. Those differences are subtle, and if you want to hear those, there are recordings out there that will play you piano pieces on a piano tuned in different systems. You need a nice hi-fi system in a quiet room to hear those, but you can hear the differences, but they're subtle. Concert pianists sometimes request particular temperaments because they're playing a particular piece that sounds best in a particular temperament. But there are much more important reasons to care about these small differences. Tunings matter because composers use keyboards to compose music. That's the instrument of choice for composers. What sounds good on a keyboard depends on the tuning, and therefore the tunings are affecting the compositions that we have. Before we get to equal-tempered tuning, composers chose different keys for different moods, because when you didn't have that gap spread out completely evenly, different keys actually sounded different. Just for an example, C-sharp minor is a key that had a particularly interesting sound. It was described in this way: a leering key degenerating into grief and rapture. It cannot laugh, but it can smile. It cannot howl, but it can at least grimace its crying. Consequently, only unusual characters and feelings can be brought out in this key. Think about that. That's C-sharp minor. On a modern tuned piano, that key sounds exactly the same as others, but on some of these older tunings, it had a particular quality, and that's how people described that quality. Now, as tunings changed, so did composition. And some of us see the mathematics as affecting the composition. Ross Duffin wrote a 2007 book called How Equal Temperament Ruined Harmony and Why You Should Care. For me, I think of this question of the tunings changing and the compositions changing as sort of a chicken and egg problem. Did the tunings change first, prompting the compositions to change, or was it the other way around? I think they really co-evolved. And so let's take a quick tour of the history of tunings, and then we'll talk about the history of music as well. Think about tunings, keyboards, but before pianos it was harpsichords and things like that. And we can look at Western music from, say, 1500 all the way to 1900. And as we look at the tunings that were used, they were spreading out the Pythagorean comma more and more equally. They had names like mean tone and quarter comma mean tone, Werkmeister 3, Kernberg 3. They had a well-tempered system that was famous by a piece of Bach, the well-tempered clavier. There was Victorian well-tempered, quasi-equal-tempered, and finally equal-tempered. And pianos were tuned equal-tempered by the late 1800s, around 1900. Interestingly, guitars, because they have frets that go across all of the strings, that makes it necessary to tune things in an equal-tempered manner way back in 1500 when guitars were first made. Now, interestingly, there's no piano and guitar music in this period, 1500 to 1900, almost none. And one of the reasons is that a guitar and a piano would have been really out of tune with each other because a guitar was tuned to a different system than a piano, until finally in 1900, pianos joined guitars in being equal-tempered. Let's look at compositions through this time period in Western classical music. If we look at early music, pre-Renaissance, it was a single voice. We're thinking about plain song music, Gregorian chant. Very few notes were used. If we move ahead to Renaissance music, it might be two simple voices together. You got early versions of major and minor scales. In Baroque music, Bach, until he died in 1750, we had multiple voices, more complex harmonies, and modulations into other keys. Classical music, up until 1820, had modulations into other keys, and those were becoming increasingly important. Early Romantic music, tonality was becoming less and less prominent. Think about the opening of Beethoven's Fifth. Bum, 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 bum. That opening motif, what key is he in? There are a lot of keys that have those two particular notes. The tonality is becoming less and less important. If we move ahead to Romantic music, think about Brahms and Tchaikovsky, they were starting to break away from old traditions. In the visual arts, think about the Impressionist painters who at the same time were moving away from realism. The composers were moving away from tonality. And finally, you get to the 20th century, you get to Stravinsky, Schoenberg, and tonality is largely or sometimes completely abandoned. Some compositions ignore any sense of sort of a tonal center, a fundamental note to base things on. Looking at the tunings and the compositions, you can see this coevolution. Tunings are moving from where the Pythagorean comma was not spread out at all to evenly spreading it out. And as that happens, composers are moving. They have access to increasing numbers of keys that sound fairly good. And over time, they lose the devotion toward a single key, and they move toward all keys being equal. Now, I want to illustrate this transition with music. And I want to go back to the two pieces we heard at the beginning. In the 1700s, Bach was composing his music, and the key of C sounded very good, and related keys sounded quite good. Now, some intervals in some keys sounded pretty awful, even in his new well-tempered system. Composers at that time would choose a key for its particular qualities. And Bach, with his well-tempered system, composed the well-tempered clavier. It's a piece in which you have a single piece in every one of the keys, the 12 major and the 12 minor keys. When you play the well-tempered clavier on an equal-tempered piano, on a modern one, you're missing a little bit of the brilliance of Bach. You see, for Bach, on his equal-tempered system, in some of the keys far away from C, he had to avoid certain intervals because those intervals still sounded bad. On a modern tuned piano, all of those intervals sound exactly the same. And so you're missing some of the brilliance that Bach had in composing the well-tempered clavier if you hear it played on a modern tuned equal-tempered piano. Fast forward to the 20th century. Now David Frome is composing 20th century style music. And for him, on his piano, all keys are equivalent. Each interval in every key sounds identical. There's no preference for any key. Keys don't have particular moods. They all sound essentially the same. And the tuning was using irrational numbers, where the half step is tuned to 2 to the 1/12th power. So let's hear these two pieces that we started this lecture off with again. Let's hear the David Frome first. Here again is the Sonata for Violin. Here's the opening from 2004. And now let's turn to Bach. Now Bach was born in 1685 and he lived till 1750. And this is the Allemande from Partita No. 2. And while I'm playing this, I want you to think about how Western scales can be tuned in different ways, none of them perfect. But these different tunings match with different music. I think that understanding Western classical music really requires understanding the mathematics of the tunings that underpin all of these pieces. Now my hope is that after listening to this lecture, you listen to classical music differently. That you hear the mathematics of tunings when you're listening to your favorite works. That you hear how all of the great composers and the works they wrote are actually affected by mathematics, and the mathematics that their tuners used, and how they chose to spread out that Pythagorean comma. So here's the Bach Allemande from Partita No. 2. Next time, we'll talk about controlling dissonance and how to tune a piano. Thanks for joining us.